Hello and welcome to another episode of the astronomy class. In this episode, we are going to talk a little bit about the relationship between physics and astronomy and how one is required to do the other. Often, when students say that they want to pursue a career in astronomy, they also miss the differences between different sub-branches of astronomy. So, in this episode, I'll try to break that down a little bit for you so that it helps you in choosing the field of your choice. Let's begin. Even before we start talking about the symbiotic relationship between astronomy and physics, it is important to understand that astronomy itself can be broadly classified, according to me, into three sub-branches: astronomy, astrophysics, and cosmology. Now, astronomy is the study of all celestial objects beyond Earth. On the other hand, astrophysics is the study of the universe and the celestial objects in it by applying the laws of physics and chemistry and even biology if we are trying to study other planets, atmospheres, etc., to see if they can sustain life as we know on the Earth. The third branch of astronomy is cosmology. Cosmology is the study of the universe's origin, development, structure, and how it will evolve in the future. What is common in studying all of these branches of astronomy is the fact that mathematics acts as the language that not just defines the laws of physics, the laws of astronomy, and helps us in creating models that we can test by applying the laws of physics and with the observations that we get through by taking the data. So we can say that astronomy deals with studying basically the motions and the positions of astronomical objects and even their velocities. Astrophysics mainly deals with how laws of physics can be tested against the observations and the theories that are produced by astronomers. In modern science, cosmology is divided broadly into two categories. Observational cosmology studies the universe using telescopes and other equipments to examine the direct evidence of the universe's development and structure. Physical cosmology, on the other hand, studies the structure and development of the universe and the physics that created it. It uses a mix of theory and experiments to construct and research cosmological models. These models are called cosmologies. They incorporate theories and the information collected by observational cosmology. Cosmology draws on advances from many scientific disciplines, including astrophysics, plasma physics, nuclear physics, particle physics, relativity, and quantum mechanics. The origin of today's cosmology began with the discovery in the early 1500s by Nicholas Copernicus that the Earth revolves around the Sun. The next step was the discovery in the late 1600s by Isaac Newton that objects in space behaved according to the same laws of physics as objects on Earth. So it is not a mere coincidence that the same laws of physics define how the planets move around the Sun as they define how will a football behave when you kick it on a field. The door to modern physical cosmology opened early in the 20th century with Albert Einstein's theory of relativity, which offered a model of space-time. Cosmologists today believe that ordinary matter, the kind of matter we interact with every day, forms only a tiny fraction of the entire universe. Most scientists today agree that dark energy and dark matter make up the larger percentage of the total energy balance of the universe. In this particular theory, dark energy makes up more than 2/3 of the universe. You can think of dark energy as something which is opposite to gravity, because gravity always attracts. Just like any object which has any amount of mass will attract other objects in its vicinity with a certain force. Dark energy, on the other hand, does not interact with matter, but it allows matter to expand into the space. So in this sense, dark energy can be thought of as anti-gravity. It is believed that dark energy is indeed the force that has overcome the gravity of all the mass in the universe, whether it's dark or not, and has allowed the universe to expand in the infinite space by what is known as cosmic acceleration. Another about quarter of the universe is dark matter. Dark matter is a hypothesized form of matter. We still don't know what it is, but we know that it behaves like matter because it has some mass. And we cannot see it, that's why we call it dark. But it is still matter because we see the influence by its gravity on the surrounding objects. For instance, in the form of lenses, which are nothing but images of very, very far away objects due to the bending of the light coming from them all the way to us. This light, when it bends around a clump of dark matter, creates such arcs or elongated structures and deforms the images of faraway objects and therefore are called as lenses. So dark matter does not emit or absorb light, and we still don't know whether it interacts with normal matter or not, but we know that it does form about a quarter of the total energy balance of the universe. Many of the other broad areas that can be studied as part of physical cosmology are the Big Bang theory, that is, how the universe actually formed, the formation and evolution of the large-scale structure of the universe. We know that galaxies come together to form groups and clusters, and those clusters come together to form even larger structures that we call as superclusters. Big Bang nucleosynthesis, which is the creation of elements heavier than hydrogen that were created in the first few seconds or first few minutes of the formation of the universe, are also part of the physical cosmology. Cosmologists also study the cosmic microwave background, which is light at around 3 microns, which was emitted, as it is believed, around 400,000 years ago, and tells us about the conditions in the universe at that time. And then, of course, it is the dark matter and dark energy. Now we know that physics is the fundamental science that deals with the behavior of matter and energy in the universe. Physics itself can be subdivided into multiple fields, many of which are required by the astronomers to study the celestial objects and their properties. Several subfields of physics such as classical mechanics, electromagnetism, thermodynamics, quantum mechanics, general relativity, plasma physics, mechanics are required by astronomers not just to study the motions and properties of celestial bodies, but also their behavior and their evolution in the future. Astronomy is the scientific study of celestial objects and phenomena that originate beyond the Earth's atmosphere. It involves the observation, interpretation, and theoretical understanding of stars, planets, galaxies, and many other cosmic entities. Astronomy often rely on both physics and mathematics to develop the theories that we rely upon today to understand the behavior of many of the celestial objects. But astronomy comes with its unique challenges. Remember, when astronomers need to observe distant objects, they need to rely on the properties and hence the interpretation of the electromagnetic radiation across all different wavebands. Because the farther is an object, the more red-shifted it will be, which means depending upon its rest frame temperature and the wavelength it emits, and of course, how far it is from us, the entire spectrum that we get from a distant object will move towards the redder wavelengths. Astronomers therefore require very unique methods to interpret the electromagnetic radiation and therefore the distant objects which are emitting them. Another way of segregating the field of astronomy is by classifying into what an astronomer is doing. For instance, I work with observational data and I call myself an observational astronomer. Irrespective of the wavelength at which the data is collected, if an astronomer is working with the images or spectra, then we call them as an observational astronomer and the field itself is called observational astronomy. On the other hand, astronomers who make use of those data, and in some cases they may not be using data at all, but only creating models and theories, whether it is to predict what can be observed if certain set of observations are not available, or based on observations which were already taken to suggest how a particular object will evolve, they are studying theoretical astronomy. The third subfield in this categorization would be the field of simulations. Simulations basically deal with computational models of celestial objects, whether it is modeling a star, because remember, whatever we are seeing, for instance, even from our nearest star sun, we are getting only the photons emitted by the outermost photosphere. So what is happening inside the core of the star is something that is created by astronomers who are working on models of the sun, or by simulators who can simulate the sun based on the observations that are already available, and then predict that for the photosphere to behave in a certain sense, what should be happening in the core. According to the NASA website, the aim of the astrophysics work is to discover how the universe works, explore how it began and evolved, and search for life on planets around other stars. Before Newton, astronomers described the motion of heavenly bodies, as they were called then, using complex mathematical models without a physical basis. Newton showed that a single theory describing what we now know as gravity simultaneously explains the orbits of moon and planets in space and the trajectory of a ball on Earth. This added to the body of evidence of a startling conclusion that the heavens are actually governed by the same laws of physics that governs the subjects on the Earth. Perhaps what most separated Newton's models from previous concepts is that this theory was predictive as well as descriptive. We cannot directly interact with distant cosmic objects, but we can observe the radiation they emit, and much of astrophysics has to do with studying this radiation and working to explain the mechanisms behind it. The first ideas about the nature of stars emerged in the mid-19th century from the blossoming science of spectral analysis, an essential mainstay in the space sciences, which means observing the specific frequencies of light that particular substances absorb and emit when heated. As the fields of nuclear physics, quantum mechanics, and particle physics grew in the first half of the 20th century, it became possible to formulate theories of how much nuclear fusion could power stars. These theories describe how stars form, live, and die. And they successfully explained the observed distribution of different types of stars, their spectra, luminosities, ages, and their properties. According to the Big Bang theory, the first stars were almost entirely hydrogen. The nuclear fusion process that energizes these smashes together hydrogen atoms to form the heavier element helium. In 1957, the husband-wife astronomer team of Margaret and Geoffrey Burbidge, along with physicist William Alfred Fowler and Fred Hoyle, showed how as stars age, they produce heavier and heavier elements, which they pass on to later generations of stars in ever greater quantities. It is only in the final stages of the lives of more recent stars that the elements making the Earth, such as iron, cobalt, nickel, silicon, etc., are produced. Another of this element is carbon, which together with oxygen makes up the bulk of the mass of all living organisms, including us. That is why astronomers always say we are all stardust. Another interesting aspect of the study of astronomy is that it is a very interdisciplinary field. While astronomy and astrophysics do apply to the study of celestial mechanics, if you want to study extrasolar planets, that is, planets which revolve around stars other than our sun, then you need to study something called astrobiology. So you will need some knowledge of biology. Also, you will need some knowledge of chemistry, which is anyways needed to study satellites such as Moon, for instance, the rocks that were brought back from the Moon mission, and meteorites, the meteors. To study these, one needs some knowledge of geology, and hence we enter the field of astrogeology. Another branch of astronomy, called astrometry, deals with the accurate positioning of objects in the sky. So it goes without saying that if you choose to study astronomy, you will need a strong background in physics as well as mathematics, irrespective of what particular subfield you choose. Also, as I mentioned in one of my earlier videos, you will develop a skill set in computing, you will improve your mathematical and logical ability, which will make you fit to apply these skills in various other branches, including industry, especially the finance sector, or in any other sector which requires mathematical modeling or heavy computing, and even dealing with large data sets. People nowadays are talking about artificial intelligence or AI everywhere. But do you know that astronomers have been applying AI since the 1980s to generate models of objects and see, for instance, how two interacting galaxies would evolve or how a star would evolve further? I hope this episode was useful to you. Please do let me know in the comment section if you would like to see more content like this and any other topics that you would like me to cover on this channel. I'll see you next week. Until then, take care.